So I get straight line in a log space. What does that mean?
Power.
It's a power law, right? A straight line in the log space is a power law. What does the slope of the line mean?
It's the value of the power.
It's the value of the power. So here, can you see from the slope of the line, is the method first order or second order?
It's first.
It's first order. It's first order. All right. And let's do it with, hold on. Let's do it for the second one. Let's actually make it a square and a red. It basically overlaps with the first one, right? I mean, you can kind of see from the symbols it's both square and circle. And let's also do it with arrow 3. Let's just do a straight line of what color? Let's do black. So now this is a second order slope. All right. Here, by the way, here I did not assume I know the analytical solution at all, right? So this is the way, like the general way of seeing how good a particular numerical approximation is. I mean, I did this right in the beginning, but this technique is going to be useful when we talk about ODE time integration. I mean, this is not even time integration yet. This is just a computing derivative. It's going to be useful when we are doing integration. It's going to be useful when we do PDEs. It's useful when we do basically almost any numerical method that actually only converges when you take a very, very fine discretization. All right. And by the way, we went only to here, right? How about going further? What do you think when you take this, keep refining?
The bottom line will keep getting lower. It will diverge.
Bottom line is gonna get lower and lower. Let's actually see if I do this for let me see, if I do this for 50 times, what do I get? And let me actually integrate the plotting into this. So great. Yes, I think that's it. So I'm just going to put the plotting also here and run it. Interesting. What's happening?
Become unstable.
Well, so we know we have analyzed what happens over here, right? As you decrease my delta t, my error goes down either first order or second order. That's predicted perfectly through our Taylor series analysis. Over here, though, it seems our Taylor series made some assumption that no longer works, right? I mean, my Taylor series analysis says that, okay, when I'm here, if I refine it another 10 times, I should get 10 times the smaller error. I should be here. Why am I here? Why am I getting bigger error? So what assumption is not true anymore? Yeah?
It's not converging.
It's not converging? Yes?
Your time step is too small and you need to account for third and fourth order terms.
My time step is too small. I need to account for third, fourth, and... But delta, if delta t is too small, if it's 10 to the minus 15, then my delta t cube is like what? 10 to the minus 45, right? Should I account for something that is 10 to the minus 45? Yes?
Maybe not.
But that, like when you try to divide by delta t in MATLAB, the arithmetic error makes it.
Yeah, something with MATLAB is actually messing up. So here we are doing math, which assumes whenever adding something, dividing something, the arithmetic is exact. But we are looking at a computer here. Okay, no computer is going to do arithmetic that is going to be infinitely exact for any numbers. So here we encounter something called a floating point representation in computers. Okay, in floating point representation, like all the numbers are represented with something around 18 digits. So imagine all of your numbers are something like 18 digits. So when you are up to here, you are basically using our formula, right? You're basically subtracting two numbers that are pretty much only different by what? 10 to the minus 15, right? So if you're subtracting two numbers that are only different by 10 to the minus 15, and each value is represented using 18 digits, then the error you are making is like 10 to the minus 3, right? Relative to the difference between these two numbers. And then, of course, you divide by this delta t, which is 10 to the minus 15. So your error is actually expected to be like 10 to the minus 3. And that's why you go up to like here. I actually don't really know what's happening here. I think, well, yeah. So usually I just see this part and this part. We need to investigate what's actually happening here. If somebody knows why. So anyway, this is another balance in any numerical calculation, is the trade-off between what's called here is we call truncation error. Why do we call it truncation error?
Because it cuts off some of the last few decimal points.
No, actually, because we are truncating this. What is this? The Taylor series, yes. This is basically, for example,
the higher order terms.
The higher order terms, exactly. So this assumes that this term is negligible, right? Assumes this term is negligible. So effectively, this approximation is truncating the Taylor series to here. And if you look at the Taylor series analysis for this, it assumes that, it doesn't assume this is negligible anymore, but it assumes this term is, actually, it also doesn't assume, it assumes this term is negligible. So effectively, this term is negligible. So effectively, we are truncating starting from here. We're truncating the Taylor series. So this error, which is larger as you increase delta t, is called the truncation error, while this error is called the round-off error, right? Because I mean, when you are representing a real number in a computer, you are basically rounding to the nearest number the computer can represent. So that's called the round-off error. So up here, we have an optimal point of the round-off error versus truncation error. So here is when you usually perform a convergence analysis for anything that you can actually round to very fine deltas. I mean, for some of the simulations, as you decrease your grid size, your simulation becomes larger and larger, so there is no way you can actually get to this point. But for things where you can actually get to this point, the correctness of your numerical approximation should be indicated by this check mark, right? Whenever you see a check mark, good sign, right? You get to the region where round-off error dominates, you get to the region where truncation error dominates. And also check the slope of your truncation error. It should be the same as whatever order you get from your Taylor series analysis. All right? Okay, so this completes our first lecture of basically we started from several PDEs and start to figure out how do we approximate the derivative in our PDE and how accurate these derivatives are. So basically this gives you all the basic tools that we are going to be using later to assess how accurate this kind of approximations are. Taylor series analysis and the convergence analysis we can do on the computer. That is going to be useful no matter if our function has an analytical solution or not.